Assalamu alaikum. Elements whose atomic number is more than 82 have unstable nucleus. These unstable nuclei tries to become stable by giving out radiation. We call such elements or such a substance as radioactive substance. To know the rate of decay of such a radioactive substance, there is a law called as law of radioactive decay. In this video, we are going to discuss about this law. For that, I considered n as the number of undecayed nuclei at any given time. Then rate of decay, that is the dn by dt. This is the rate of decay is found to be directly proportional to number of radioactive nuclei present at that moment, at that instant. Here, let me repeat this once again. Here, dn is the number of nuclei undergo decay in time dt. So when we divide these two, we get a rate of decay, which is found to be directly proportional to number of nuclei present at that moment. Understand? Now from this relation, see, we know very well, if we have proportionality, on the removal of this proportionality, we have to include a constant. So the same thing I do here. Plus dn upon dt. I introduce equal to sign. Along with that, constant is introduced here. Then yeah. This constant is called as proportionality constant. Here I name this constant as the lambda. Lambda. So dn by dt is taken as the place of a constant. I write lambda. Then n is written as such. Here I introduce a negative sign here. This negative sign represents that as the time goes, the number of n value decreases. The number of nuclei decreases as the time goes. This is what it means. Okay. So the same thing I do here as well. Write minus sign. This minus sign shows that with the time n value decreases. Okay. Here lambda, which is nothing but proportionality constant, has got a name. Here lambda is nothing but decay constant. Decay constant. Or sometimes it is referred as disintegration constant. Both decay and disintegration represent the same thing. Okay. Now, to get the total number of undecayed nuclei at any given time, I integrate this term. So, n value can be obtained by integrating this term. Now, before integrating this, I am going to make certain changes to this. What is that? I'll rewrite this one as dn divided by n. Here I have brought n this side. Then dt is taken that side. So what I'll get? I'll get this minus lambda dt. This is what I get. After that, I'm going to integrate. On integrating, the above equation is integrated to get the value of n. Okay. So, integral of dn upon n equals to integral of minus lambda dt. Here, if I consider that at a time initially t is taken as 0 second. When time is 0, that is initially the number of atoms or number of nuclei of those atoms is taken as n naught. At the beginning, number of nuclei are taken as n naught as a time t. As the time goes, a time t, that is taken as n, number of nuclei at any given time t. Okay, so I am going to provide limits to this integration. So here lower limit is n naught and upper limit is taken as n. Similarly, at time t equals to 0, we have n naught number of nuclei, and when time is t, number of nuclei is taken as n. Okay, so when I integrate this, see what I get on integrating this kind of term. So suppose I have integral of dx upon x, then I will get natural log or log of x to the base e. This can be written in otherwise as natural log, log of x, natural log of x. Okay, so there are two methods of writing natural log. Either you can use ln, or in the place of that, log of something to the base e. When we have base e, it means that log is natural log. Clear? So by using this formula, I am going to integrate this. So I'll get this expression. Natural log of n. Okay, and here we have the limits. Limits are written outside the bracket. Lower limit is upper limit. This one to be equal to. Now I am going to integrate this. Here, minus lambda is a constant, so we cannot integrate the constant. So it is taken out, and we will integrate only this term dt. Okay, what is the formula is used to integrate this kind of term? Here, see, integral of dx. This is nothing but dx. So this I am going to, this method or this formula is used here to integrate this part of this equation. So the next step, okay, natural log of n, or is n naught n here is equal to minus lambda. After integrating this, you get t, and outside the bracket I am going to write the limits. Okay, lower limit and upper limit. Now I am going to substitute the values of upper and lower limit. You see how I do it? Yeah. In the place of n, I am going to write the upper limit. Then in the place of n, again I will write the lower limit. Okay, n minus n naught. Now let me increase one step here for a better understanding. In the place of n, I have written the upper limit. Then I subtract this. Then in the place of n, I am going to write the value of a lower limit, that is n naught. This is what I get here. Okay. By substituting the values of these two, I have to subtract them. Just remember. Then here, minus a lambda. Inside the bracket, I am going to write the value of t. Upper limit t minus lower limit of t is 0. Okay, this is what I get here. Good. The next term, this term can be written as here in a log, when we subtract, in log, the subtraction is just equal to division. So this can be written as log of n upon n naught. And this one to be equal to minus lambda t. Okay. Here I told you earlier, natural log can be represented in another way as log. I written that one somewhere here. Okay. By following this one, this can be represented. Okay, let me leave it as such. So natural log of n upon n naught equals to minus lambda t. Okay. Now I take the exponential of this equation. Now take the exponential. I get the equation something like this. Here. Taking exponential. Of the above equation. Taking exponential of the above equation. What I get? I get this. Here this side, this will disappear and I'll have only n upon n naught. And this side, this term will get raised to the power of e. Okay. This is what we obtain on taking the exponential of the above equation. The next, this can be rearranged and written as n equals to, here n naught is taken to the other side, so it will multiply n naught e power minus lambda t. This is the final expression and it gives us law of radioactive decay. So what do we understand from this equation? Here this equation clearly shows that the number of undecayed nuclei depends on the number of nuclei present at the beginning. Okay, this is what we understand here. And the second thing, it shows that nuclei undergo decay in exponential form. This I am going to show with the help of a simple diagram. Okay, I will draw a graph here by taking time period, half-life along, or it's a time period along the x-axis, and number of undecayed particles or number of undecayed nuclei along the y-axis. By doing so, the graph obtained is something like this. You get an exponential curve which represents this equation. N is equal to n naught e power minus lambda t. This is what we obtain. Okay, so actually here first half-life period we have this n becomes n half. Okay, then the time period, which is twice of t half, we have number of nuclei becomes n power 4 and it goes in the similar way. I will get one more. Yes, 3 times half-life period of the given radioactive substance. Now at a 3 t half, number of nuclei is going to be n divided by 8. So this clearly shows that as the time go, nuclei decay exponentially. But here, if you observe this graph carefully, you may find that the curve do not touch the axis. At this point, it goes almost parallel to the x-axis. It means radioactive substance taken in bulk quantity have infinite lifetime. So we cannot predict that which nuclei is going to decay. Okay, that cannot be predicted. One nuclei may decay, another nuclei may not decay at that time. So it cannot be predicted. So to measure or to study the decay of such a radioactive substance, we have this law. I hope the video is useful. If you have any kind of a doubt relevant to the topic, can you put your questions in the comment section? Thanks for watching.